Forest fires cause $16 billion in damage and are responsible for hundreds of deaths annually. Research has shown that early detection is critical in limiting damage. I evaluated existing fire detection approaches in 3 categories. CO2 sensor networks require thousands of devices to provide thorough coverage, making them impractical. Optical systems use expensive hardware and lack the ability to precisely localize fires. My proposed FireWatch device extends optical systems to achieve all 3 goals. Here I list out 7 design objectives with a specific test and criteria for success. I'll start by going over the device's hardware. Inside the main body is a Raspberry Pi, cellular antenna, and a battery with a solar panel mounted on top. The device uses 4 1080p cameras mounted on a separate camera hub. Using CAD software, I designed and 3D printed the housing and camera hub. The total bill of materials is around $103, successfully meeting the cost-effectiveness design objective. Now I'll go over the main software components. 4 images from the camera sensors are combined using a panoramic stitching algorithm. This single image is inputted into the fire detection model. I couldn't use current state-of-the-art wildfire detection algorithms since they weren't designed for embedded systems. To solve this, I developed a novel technique called data sparsity, which leverages the fact that most pixels in an image aren't relevant for fire detection. To induce this type of sparsity on the input image, I run the image through an attention network which produces a saliency map. Endpoints from the map are then sampled and then are run through an encoder and decoder network to output a classification and pixel coordinates of the fire. After training the network, I evaluated performance on real wildfire footage in the HP Red dataset. The results show a 3 to 6x improvement over current state-of-the-art in both power consumption and memory usage, while maintaining equivalent levels of precision and recall. This gives us an F1 score of 0.92, satisfying the detection reliability design objective. If a wildfire is detected, the system then needs to be able to convert the pixel coordinates to GPS coordinates. With just camera data alone, this is impossible. But the key insight is that if we find a Google Earth rendering taken at the same location as the camera and perfectly aligns with the camera image, we can define a mapping from pixel coordinates to latitude and longitude. To find this aligned Google Earth rendering, the module repeatedly queries Google Earth with an orientation to receive back a rendering. For each rendering, Harris corners are computed and a transformation is calculated between the rendering and camera features. I use an upper confidence tree search algorithm to efficiently explore the state space. Results on the same HP Red dataset show 86% alignment success rate and an RMSE of less than 50 meters when a match is found. Additional tests for battery life, flexibility, and water resistant were successful, meaning I met almost all my design objectives. As a final test, I installed 8 FireWatch devices in the Blue Ridge Mountains. Over the 5-week testing period, 7 of the 8 devices remained functional, and 1 of the devices was able to successfully detect and localize a forest fire. The accurate detection of a real forest fire is strong evidence of FireWatch's efficacy in a real-world setting.